From our perspective, what we've just done, we've spent close to about an hour setting the foundation for representation, right? We haven't talked about sequencing or thinking or what is required to solve. We're simply saying, how would you see the board? And then when you see the board, what can you do with the board? And then given what you have to do with the board, what are some of the tools or tricks or hacks or techniques that you can use that allow you to reuse lines or codes or programming or functions that you've already written to address one type of functionality on the board. And rather than rewriting it all over again, what are you doing? You're simply flipping the board so that you can use the same line, the same sequencing without having to rewrite it all over again for a different orientation of the board. And this insight comes to you how? This insight comes to you because you're simply saying the machine doesn't have an orientation. The machine doesn't have to think in terms of, left, right, top or bottom. The machine just has to think in terms of coordinates. And as long as you can bring the coordinate system in alignment with the code, the code would work. What is this? This is design. This is a design choice. How did this design choice become possible? This design choice became possible because we didn't think in terms of our context. We thought in terms of how the machine, how the code, how the math, how the engine, how the AI sees the world. And the key, the trick to that was the representation of the board, the representation of the Scrabble board in a grid/coordinate system. So now think in terms of what is the amount. If you have the board sorted out, the next question that comes up is, how do you do work? How do you do work on the board? What is the work that you have to do on the board? What is involved in the work that needs to be done on the board? And in that work, I think we've got about maybe 6 or 5 items here. So there's word generation, on which you've spent time. There is the placement of that word on the board. There is validation. When you may have a valid word, but can you actually get valid placement of that word on the board? So when you place that word on the board and you sort of marry it or tie it or put it together or connect it to its anchors, at that connection, at the point where the anchor meets the word, is that combination still a valid word? Then you also have to think in terms of placement. When you look across all possible combinations, all possible marriages or meeting points of the anchors with your word, do they represent valid placement? And then you do a collective scoring. Right? You've got 5 elements here that you're trying to calculate and work together: generation, placement, validation of both word and placement, and then doing a collective scoring of the word that you're trying to work with. Look at just the first piece. I look at just the first piece, right? Which is this piece, which is word generation. Actually, I can do more. I can actually do word generation and word validation. So I think from that perspective, I've got 2 pieces that I can solve using the tool or the technique I'm going to now discuss. What I want to do is I want to tackle 2 problems. I want to tackle number 1, which is word generation, and I want to tackle number 2, which is word validation. One of the tools that we use for this is trees. And for now, we're still in the representation space, right? We're still in the representation space in the sense that we're saying, previously we just walked through the representation of board. Now I'm going to walk through the representation of the dictionary. And the representative dictionary is done through a tree. So for example, here I've got 2 things. I've got a small sample of a dictionary, and in this dictionary I've got 1, 2, 3, so ace, aced, acer, and then 1, 2, 3, 4, so that's 7, bar, bear, bared, and beer, and then 1, 2, 3, car, care, and cared, right? So I've got 3 plus 4, that's 7, and 3, I've got about 10 words. And what I want to do is I want to see, okay, if I just take a look at the first sample, so in this specific case, A, C, and E. And A, C, and E is the first word, right, which is ace. And then I've got a second word here, which is bar, which is B, A, and R. And this is the second word, and that's bar, right? So what I've done is I've created a tree, but this is a tree that rather than have numbers, it actually has words. And I can sort of use this tree for multiple purposes, but it's one possible representation. And when I'd asked you earlier, if you think in terms of how we normally look for or search for or validate a word, essentially validation requires what? I have a word, for example, ace, and what do? I do an index search on Excel using my Collins dictionary, and I search through all the words. So I look through all the A's and the C's and the E's till I find that yes, I actually have a valid word called ace. And if I have a perfect match, exact match with that word, I tell you this is a valid word and I return you a 1. Okay. But for trees, right, in this specific instance, the search model is different. So now what I've done is I've taken the same thing, and some of you, those of you who've read the fastest Scrabble program in the world paper that was assigned reading, I think in your second and third week, and now also for your fourth week, if you've seen, you must have seen this before. So now what I've done is I've taken that same concept that I discussed earlier, which was those two-step trees, that tree that represented 2 words, and use it to represent this entire dictionary. So all of these words, right? So for example, C-A-R is one word, C-A-R-S is another word. And you can see here, the double circles represent the end of word in this specific representation. C-A-T and then C-A-T-S, cats. So that's 1, 2, 3, 4 letters, and then 2 words, and then 1, 2, 3, 4 letters, and 2 more words. So collectively, this is about 4 words. This branch that you see here represents 4 words. And then you've got dogs, and then you've got done, and then you've got ears, and then you've got eats. You can see that, right? So now T-R-I-E, tree or try, is essentially a tree that uses letters or tiles, and we can use that to store a dictionary. And then we can also use it to both validate or search through a dictionary. And we'll explain how does that work, right? So we're going to walk through the process of how does that specific thinking works. All right, so now if I look through that dictionary, this is a sort of a simpler, easier representation. How do you search for a word? So for example, if I have a choice of tiles, and those choice of tiles sort of gives me the word aced, A-C-E-D, and I'm wondering whether A-C-E-D is a valid word, how would the search process work? How would I use the tree or try to get to that word? So obviously I start with the first letter on my tile or on my list or on my word, and now I'm looking at specific problem, right? My specific problem is validation. So from a validation perspective, I see, okay, A, what's the first letter A? Do I have an A? I have an A. So I come here, so I have an A. What's my second letter? My second letter is C. So I have a second letter C. Do I have a second letter C? Yes, I have a second letter C. So now I have AC. Then what's the third letter on my list? It's E. So I have ACE. So now I have a third letter. And yes, I have a third letter, ACE. And then I have a fourth letter, and that letter is D. And even though ace is a valid word, I want to see if there is another edge that leads from ace, which has a D. And yes, I have a fourth letter that leads to, and I've gotten to the end of the tree or at the end of the word, which basically tells me that aced, A-C-E-D, is a valid word. Now, if you remember when we spoke about indexing and we spoke about searching, think in terms of search on Excel. How do we validate a word? How do we validate a word? We validate using an index. But in Excel, how does that index work? So in Excel, when I search for, let's say, aced, A-C-E-D, what's going to happen? It's going to come to the first word, say, okay, is this ace, A-C-E? No, it's not. So actually do a word-by-word comparison. So it's going to take A-C-E-D here, say, is it the same word? No. And repeat it here, no. Repeat it here, no. Repeat it here, no. You're going to go through all of these words. And, by the time we get to number 23, we've done 23 comparisons, and all of those comparisons saying no. And let's assume ACED is where? ACED is, let's say, at position number 900. Now, if ACED is position number 900, every time you search for ACED, what are you going to do? You're going to do 899 comparisons that are not needed. Compare this to this approach, the approach that I'll be doing with tries or trees. What's happening here? We start with the first word, which is A. Then we see, okay, what are the valid combinations that go? And in this specific small dictionary, you know, all the combinations that we have are ACED. We're going to look at other examples a little later where we have a more complex tree. But all we need to do is basically search through the next letter on our list for our whole word generation combination and see whether we have the right letters that we need in that list, and if we do, then that's fine. And then you can, right now we started with ACED because we had that word and we were wondering whether that's valid or not. But think in terms of how would word generation work. So let's say I have an anchor A, and I want to see, okay, if I use A as a prefix, right? So for example, let's take the first word. Just take the first words or the first two words, right? So the first word in this case is ABC. Let's take this, ABC, right? The first words in this are your prefix, and the words that follow are suffixes. So I can actually break my search problem into two pieces, prefix and suffix. And I can match the prefixes and then say, okay, what choices of words do I have that start with an A? And the choices of words that I have are aced and acer. Now, if I'm looking for aced, I'd say, okay, the next word that I have, the next possible choice that I have in my graph, in my tree, is a C. So do I have a C? Do I have a tile C, or do I have a letter C or an anchor C on the board? And if I have it, then okay, I have two. Then what's the next possible choice? The next possible choice is E. So do I have that? I have that. If I don't have that, you know, it stops. You know, okay, so I can't move beyond. So let's abandon this chain of thought. Let's look at a different possible combination. But if I have an E, okay, so then what else do I have? Do I have a D or an R? If I have a D or an R, then yes, I actually have two words. And then of acer and aced, ACED is a higher scoring word compared to ACER, and that's what I'm going to pick and choose. Now I've done it two ways, right? I have a valid word. I have a word I want to convert or confirm whether that's a valid word, and that's how I search for it. And second one, which is the other approach that I've just done with you, is a different approach where I don't have a valid word. I just have a starting anchor, and that anchor is A or B or C. And I'm using the tree or the try to generate that word. Do you understand the difference between the two approaches? Given a word, validated. Given a tile, see if there are valid words that match the list of tiles that you have on your rack, so that you can find out if there's a valid word that you can place on the board. First focus on the concept. What is the concept? The concept is index. What is an index? An index allows you to search through a sorted list of data. What is a sorted list of data? The Collins Scrabble Words Dictionary is a sorted list of data. How is it sorted? It's sorted, the first letter is AA, the next is AAH, then it's AHED. So if you think another, it's sorted alphabetically, right? It's sort of every increasing letter that comes in later. So for example, the A's come first, then the B's, then the C's, then the D's. So far so good. Now if you have a sorted list, how do you search a sorted list? There are two ways of searching a sorted list. You could take these AAs, right, and turn that into a numerical score or a representative score. That will sort of give you a sense of what the word looks like. Alternatively, you could think in terms of how is this indexed? It's essentially indexed in terms of, you know, I have a starting point, which is the first letter. Then I have a second letter. Then I have a third letter. Then I have a fourth letter. So if I'm searching for it, what I want to do is I want to do a letter by letter search, which basically means that if my first letter is an A, I only want to look at that part of the tree that has a A in it. If my starting point is a D, then I only want to look at that part of the tree that has a D in it. Remember when we started this discussion right at the beginning, what did we start off with? We started off by saying, what if you broke the Collins dictionary down into 26 columns, and each of those columns represented a letter of the alphabet? So you would essentially go from A to B to C all the way to, let's say, Z. You were creating 26 different searchable columns that made it easy for you to jump directly to the right column when you looked at the word Z, or for example Y, or X, or W for that matter. What I'm saying is, I'm simply saying, rather than doing this in Excel, what would be an equivalent representation? The equivalent representation is you just build a tree. Actually build a tree that starts with all the letters A. So let's have, I have a tree, I have an A tree, right? Then I have a B tree, then I have a C tree, then I have a D tree, then I have an E tree, then I have an F tree, right? So I have a tree for all of them. So I have a long list of trees, and then what do? After building that long list of trees? So what I do after building that long list of trees is I simply say, you know, this is my A tree, this is my B tree, my C tree, this is my D tree, E tree, F tree. What do? I simply merge them together into one big tree. And when I start my search, you know, I say, okay, what's the first letter that I'm looking at? So for example, here, my first letter that I'm looking at is an H. So it's A, B, C, D, E, F, G, and H. Now, in the Excel indexation, right? In the Excel indexation, what would happen? I would search through all the letters that came before the letter H, or I, or J, or K. I couldn't get to this point if it wasn't possible for me to break it down. But now what I've done is, I've actually broken down. So rather than going through all of this part, I ignore the rest of the tree and I go straight to this part of the tree. And this part is, okay, my first letter is an H. Okay, now, what's the next letter? So let's say my next letter, so H-I-A-K-G-E-T, right? These are the word choices I have. What are some of the valid words that you think you can generate from this? One word is hike. So H-I-K-E. Let's say I have this word. I think this is a good word. I would explore whether this is a valid word. So what would now happen? I'd come to my tree or my try, and then what do? I say, okay, H. So I have my first word is H, first letter is H. Now, is there an edge? Is there a path? Is there a branch of this tree that has the letter I? So yes, I actually have one that has an I. And then on that path, is there a tree or a branch or a edge that has the letter K? Yes, I do. And then on that path, is there a tree or a branch or a list or an edge that has the letter E? And I do. So it's H-I-K-E. And if this is a terminating node or an end of word, then I know for a fact that hike is a valid word. And there you go. Now I have hike as a word. Does that make sense? Now in this, A, B, C, D, E, F, G, H are prefixes. And this, the I-K-E, is a suffix. So this is a suffix, a word that comes after, a part of the word that comes after, and this is a prefix. And what we've done is we've broken the search down into two pieces. We're using the prefix as an index to get to the starting point, the right, the relevant, the fastest starting point for words that begin with that specific letter tile. And then we see if there is a match with suffixes. In the tree representation of the dictionary, are there branches that map to the words that follow? You'll find, if you look at computer science literature, you'll find that tree search is generally quite fast compared to, even if you think in terms of indexes, you know, how do you search indexes? You'll find that indexes also use tree search. You've done word gen in Excel, you're comfortable with word gen in Excel, you understand how word gen in Excel works. This you haven't done. I wouldn't recommend that you implement this in Excel. I'd recommend that, you know, because you're doing introduction to programming, whatever language, I think you're using C++, whatever language you're using, you know, just do two things. Do a tree search, break this down, right? Forget Scrabble as a game. Just take the Collins Scrabble dictionary and implement. You've read the paper, the fastest Scrabble program in the world. You've also seen maybe 2 or 3 different representation of that paper as video lectures, and I think there are a couple of Medium articles floating around that talk about the implementation of that. You'll find a lecture in Carnegie Mellon. I think you might even find a lecture at MIT that sort of cover the implementation. Just convert the Collins dictionary into a tree or a dog, and then write a routine or a program that validates and searches for a word in that tree or a dog, and then just run the two side by side. Simple experiment. It's a hard experiment because you just started to program, right? But it's a good self-side assessment assignment. It'll teach you how to program Tries and DAWGS. And even though you may not understand all the nuances of these two structures, but it'll teach you how to program it, and then you can just compare performance of, when you search for a validation of a word or generate a word using your Excel model, even using Power Query on Excel versus Tries and DAWGS, which one's faster. And you'll find that in terms of repeated searches or repeated pings, you'll find that this is more efficient. We'll talk about, why do we think this is the case a little later. We've got this specific dictionary. We've done a simple implementation. What would something a bit more complex look like? Dictionary is a lot longer. But if you just look at the A and B side, right? I'm going to pose a very quick challenge and question to you. What's the highest scoring word that starts with a B in this specific try? This is the tree. Find me the highest scoring word that starts with a B or has a B in it. So where do you start? You want to start the highest. So the relevance piece of this is, you have a list of tiles, you have a rack of tiles, and one of those tiles is a B, right? So you want to say, okay, or an anchor, which is a B, and you want to say, okay, what is the highest scoring word that starts with a B? So what you're saying is, my prefix is a B, find me a combination of suffixes that give me the highest possible word. Now, the sequencing of this is, you think in terms of B. So B has three branches. One is this, which is A, E, and O. You have to traverse all three branches. So BA by itself is a valid word, but obviously that's not a highest scoring word, right? And because it's not a high scoring word, it's possible that it's not, because there's two, the reason chance it's not a high scoring word. Then you got B-E-A-R, end of word. So this is one word. Then you got B-A-R-E-D, bed. This is another word. Then you've got B-E-E-E, another word. Then you got B-E-E-R-S, third word. You got B-O-R-E-D-O-N-M. There we go, boredom. Do you see how search works now? And the same question, exactly the same question that you've just answered now, could also be answered with a different question, which is, high scoring word that starts with a B, D, and M. In this case, we're saying that you actually have a slate that has the word B, D, or M, or anchors that have the word B, D, and M. And can you find that word? And how do you find that word? Two ways. If you actually have a dictionary, you can sort of manually go through this dictionary, search for the high scoring word, and then look for that word. But in that case, what you need to do is you need to say, okay, my assumption is that the highest scoring word, starts, it has more letters. But if all of them are letters or tiles that score 1, then that doesn't necessarily work. I may actually have a 2-letter word that has Z or Q or X in it, and that'll be score much higher than, let's say, a 4 or 5-letter word. Second option is to search through the tree. On that full tree, if I say, what's the highest scoring word? How would you search for that? The game AI is going to generate a list of all possible valid words, then rank them based on their score, then think in terms of their placement, then think in terms of, what is the best possible optimal placement that generates the highest possible score. But it's going to do it step by step in sequencing, right? The first step is word generation and validation. Have a list of valid words, then have a list of valid placements, then have a list of valid placements on the board, then have a list of the highest scoring valid placements, then sort of figure out, what is the best possible move. And then he has to do this within a certain limited amount of time that it has available as far as the engine is concerned. There are combinations where you would think that a triple word, TW, would dominate and would be a better placement for, let's say, something like an X or A. But you'd be surprised to know that, a a DW, which is a double word, combined with a DL, which is a double letter, sometimes actually leads to a higher score than just a TW by itself.